In this video, we will focus on objects that undergo uniform acceleration, and for those objects, we will be deriving what we call as the three equations of motion. So in a sense, we are going to focus on this velocity time graph that we just plotted in the earlier video. So let's get started. It's going to be three equations of motion, and for us to start deriving those equations, let us take a slice of this this particular graph. So what this graph says is, an object that was at rest at time 0, right? Here it is 0, the velocity 0 at time time 0, and as its velocity increases at a constant rate, because the acceleration is uniform, right? As it accelerates, and its velocity at the different points in time is what is plotted here, and this is a straight line, right? Now let's take a slice of this, maybe something like So let's take a slice of this, maybe something like this part, and let's try to magnify that. So it's going to look something like this. So on a graph, here is your velocity, and this is time, and you're going to have the object. So when I'm going to look at this particular slice, so this is going to be a starting time, and this is going to be the ending time, and this part is actually the initial velocity at the starting time, and this is going to be the final velocity at the end time, right? So if you call the start time as t1 and the end time as t2, and this is going to be your initial velocity, which we'll mark it as u, and let this be the and if we denote the final velocity as here, and if we call the final velocity as v, right? So this one is u, and this entire thing is v, and yeah. So this object is the velocity of this object has increased from u to v between times t1 and t2, right? Now and let's also mark the endpoints of this. So let's say that this object moves from point A to point B, and this part, the origin, let's call it as O, and let's call this point as C, and this point is E, right? Now, using this graph, right, using what we have just called here, we'll derive the equations concerning acceleration, distance, and velocity, right? So what is acceleration? How do we calculate the acceleration from here? We know that the acceleration is equal to the rate of change of velocity, which is the change in velocity over time. Change in velocity over time. Over time. So in this case, your change in velocity is going to be the object's final velocity is v, and it started with u, so it is going to be v minus u divided by t2 minus t1, right? Now, if you notice here, acceleration only concerns with the difference in the time. I mean, between between your starting time and your ending time, right? So you don't have to keep it as t1 and t2. We can consider this as 0 and t, right? So the time, it's only the elapsed time that we're concerned to find the acceleration. So instead of this, we can rewrite it as v minus u by t. If we can call the origin as 0 and this one as time t, right? So I'm just considering the difference between T2 minus T1 as T. That's it. So that's how the graph is being plotted here. Right. So your first equation is your acceleration, Z of acceleration, where your acceleration is defined as v minus u by t, and you can rearrange this equation which states that v is equal to u plus at. So this forms your first equation of motion. Yeah. So this is my first equation. Now let's go to the second equation. Now that you have derived the velocity from the initial velocity and acceleration, let's try and find out the total distance covered or the displacement. Both are the same, primarily because this object is moving along a straight line, and it's not coming back, right? So it's in instance we are considering objects of this kind. Right, objects of this kind, where it keeps moving towards the moving along the straight line, and it's not coming back, or it's not taking a circular path. It's just going straight. So, when an object exhibits that behavior, the distance and the displacement would be the same, right? So, so coming back. So what would be the distance covered by this particular object between these points A and B here, right? So that's what we are going to capture. So what is going to be the distance? And we call distance by the letter S. Right? Now, if you notice the specific graph here, at time 0, at the starting point, it was traveling at the speed of u, which means that for every unit time here, it was covering a distance of u. That's what speed means. Speed or velocity is distance or displacement over time, which means that at this particular point in time, this length gives not just the velocity, but it also gives the distance covered by this object at this particular time. Similarly, right next to this, if I draw a line very close to that, right, something like this. If I draw a line very close to that, very close to this specific line, this length will be slightly bigger than this, and what that would give me is the distance traveled by the object, the distance covered by that object at time that is slightly outside of 0, right? So if I keep drawing this line close to one another, what I will have is the velocity at every point in time, every unit time. So if I'm drawing this very closely such that each point gives me 1 unit time, it means that this height does not only give me the velocity at that unit time, it also gives me the distance covered at that unit time, right? So in a sense, the distance, if you were to calculate the distance, total distance covered by this object between points A and B, all what we need to find is to draw these lines close to one another per unit time up until between 0 and t, and which is also going to be the same as the area of this trapezium, right? So in a sense, your distance can be calculated as the area of the trapezium OCBA. I'm calling this trapezium OCBA, right? So that's what is going to be my distance. Now let us try to calculate the area of this trapezium. We know that this trapezium has two parts. There is a rectangle. There is a rectangle and there is a triangle here, right? So which is basically your area of rectangle OCDA plus area of triangle ADB, right? Now we know that this area of this rectangle is going to be this distance is t and this one is u, so it is ut, right? Plus we know the area of this triangle is going to be half of the base times height, right? The base is this, which is v minus u, right? Times the height. Height is AD, which we know it is t. And we know that v minus u can be written as, from this equation, v minus u can be written as a times t. So it is going to be half of at square, right? So distance s is equal to ut plus half of at square, and this is our second equation of motion. Right. So we have now derived the second equation of motion. Now let's go to the third one, and to derive the third one, we will still try to calculate distance, but we'll calculate the distance in a slightly different way, right? So the distance is going to be your distance yes is going to be your distance of S is going to be the area of trapezium OCBA, and this time we will not split it into this into a rectangle and a triangle, but rather we will. There is a formula for calculating the area of the trapezium directly, which is half of these two parallel sides, which is the length of OA and CB. So it is basically going to be OA plus CB times the distance between the two parallel lines, which is going to be OC. OC. So let's try to calculate this. So this is going to be half of OA. OA is U, right, and CB is V, right. So it is going to be U plus V times OC is going to be T, right. So this is my thing here. Now we know that T can be replaced. Sorry. So we know that this letter, the value of T can be replaced from the first equation, which is if you bring T this side, it becomes T is equal to V minus U over A, right? So which means that this equation can be rewritten as half of U plus V times V minus U over A, right? So if I rearrange this a bit, what happens is if I bring this to A, now if I bring this to A on the left hand side, it becomes 2AS is equal to, you can rewrite this as V plus U times V minus U. And which means that you can simplify this as 2AS equals V square minus U square. So this is my third equation of motion. Right. So we have derived the three equations of motion here. We started with the first one, which is V is equal to U plus AT. Then we tried to calculate distance, and using the area of trapezium, and then we also captured. We can also calculate the distance without time. So that is this variation. And just to recap, all the three are applicable for objects that undergo uniform acceleration. So that's going to be the key. So it is all for uniform acceleration. Objects that undergo uniform acceleration. Right. So with this, we are almost at the end of the chapter motion, and there is only one small idea that we'll quickly explore before we move on to the solving the in-text questions and the exercises. So far we have been looking at objects that has been that has been moving along a straight line, right? So it's always on the straight line, correct? Now, objects, as we discussed in the beginning of this chapter, that objects movement can be very different, right? Not every object moves along a straight line. So we will consider one variation here of an object that takes a circular path, something like circular path, and it is also undergoing uniform. It goes through. The speed of that is constant, right? When it takes a circular path and with a constant, with a uniform speed. Let's take that way. So an object moving along a circular path is something like this, right? So it moves, it goes like this, and yeah, so that is how this object moves. It starts from a point A and it takes a circular path, right? Now, how do you calculate the speed of an object that takes this circular path? Now, let's consider this. No, it makes a circle of radius r, right? Let's consider the radius of the circle to be r, right? Now we know that speed is going to be we know speed is going to be distance covered over time. Right. So in this case, the speed of the circular path, you can derive that by if you know the distance covered by this particular object. So we know that the object takes a circular path, and we know that the distance covered is nothing but the circumference, the length of the circumference of that circle. So the length of the circumference, we know that it's 2 pi r over time, right? So that is the speed for if you were to calculate the speed of an object that takes a circular path. This is the formula that we would apply. So I think with this we have completed our first chapter, which is motion, and in the next video we will start solving for the in-text questions, and then we will also go over the exercise questions.
One final thing before you leave. If you wish to revise the concepts that you've just learned, please look up and try out the free Revise app bot on Telegram app. Telegram is available for free on both iPhone and Android. Also, if you did like the content that you just watched, please do like, share, and subscribe this with your friends. Thank you.